Hello, everybody. As Dominic just introduced me, my name is Naghmen, and I'm a graduate student in software engineering group in computer science department. Today, I will talk on reliability and safety of the medical systems. So this is the outline of my talk. First, the motivation for this research, and then just a brief description of the safety critical systems, which is the category that medical devices fit in. Then there is a case study of one of the accidents because of the malfunction of one of these safety critical systems. Then just an overview of the FDA regulation for medical software, and then liability issues of medical systems. Then I will just go a bit to the technical issues for software reliability techniques, and a kind of case study of the reported medical software failures. Then I just briefly discuss about the future direction in this research area, which is one of the hottest area in the reliability research right now, which is autonomic computing or self-healing. And then I will conclude my talk. The dependence of the health industry to the computer system is increasing every day. They use the computer systems for patient treatment, patient information management, financial management, or operation management. Even for a device with numerous mechanical and electrical components, usually the software development takes about 70% of the project budget for its development and for the quality assurance. And now, looking at the medical software in particular, we consider those systems in the category of the safety critical systems. So what is a safety critical system? A safety critical system is a system which, if it malfunctions or if it executes erroneously, it will result or it will cause a serious or loss of injury, like serious injury or loss of life for the people, or damage hugely the environment. So the hazard of a medical software is a situation in which there is actual or potential danger to people or to the environment. And in order to calculate the risk of a medical software, it's a product of the severity of the injury and the probability of its occurrence. Now going into a case study, which is very famous and most of you are familiar with, which is Therac-25. Is a very famous example of an accident which resulted from a fault or a small fault in the software of this system. So the Therac-25 is a computer-controlled radiation therapy machine. In between the years 1985 and 1987, it massively overdosed 6 patients over North America. The operation of the machine is based on the linear electron acceleration. So it has 2 modes for therapeutic reason. One of them is the X-ray mode. The other one is electron mode. So just a brief explanation of the structure of the Therac-25. So there is a turntable in this machine, which was the reason of most of the failures of the system. The rotation of this turntable actually put the different equipments in the beam path that may result in producing 2 modes, which is electron mode and the X-ray mode. So the position of this turntable is controlled by 3 microswitches. And so these microswitches define which equipment should be in the beam path in order to produce the X-ray or the electron mode. 2 important bugs of the system after all the analysis and the recall of this system. 2 important bugs were found out in the Therac-25, which are known as Tyler bug or Yakima bug. Both of them resulted in an unsafe operation, which means that the turntable position was not in the correct position in the beam path. For example, we wanted to produce an X-ray mode, but the equipment which should be between the beam path and the patient was not a right equipment. So although at this time that these bugs actually appeared and the error appeared in the system, there were some messages given to the operator which says that, for example, the system is malfunctioning. But the error messages were cryptic. That means that the operator of the system didn't have any idea what was that error mean. So it just proceeded with the operation. So the error source of both of these bugs is one of the important issues in the software development, which is controlling the concurrent access to the shared memory. If you cannot control this concurrent access, it may result in a race condition and probably an error in some execution path. So this is a general operation display of the Therac-25. The operator enters the patient name, patient input data. It defines the treatment mode, which could be X-ray or electron mode, and gives the type of the beam and the energy associated to that mode, and the rest of the information. After all the information gets input to the system, then the cursor will come to this command line, which means that all the data had been entered in the system, so the system can parse the data and actually start up operation. So looking at the internal software structure of the Therac-25, it has 8 procedures for the operation. So just briefly explain how this error happened. There is a data entry procedure, the number 1 procedure, which is responsible for actually getting the input data and parsing it and then scheduling the operation of the system. It communicates with the keyboard handler task through a shared variable which called data entry complete. This data, as soon as the data entered into the system, the flag of the data entry complete is set, and thus we execute the data entry procedure, and then we go towards the setup test procedure. So at the same time, the keyboard handler parses the input data and put the input data into this shared into this variable. The higher the higher byte of this variable actually give some input data to the data procedure, data entry procedure, and the lower byte is define the position of the turntable. So if the data entry flag, the shared variable, gets set before the data for the position of the table gets updated, then there is then the procedure going to be exited from the data entry procedure, and thus does not realize that there was an update in the, for example, in the data which was entered. So getting back to just the operator display, just trying to simulate what was the error, is that assume that the operator entered some data and then comes to the command line. At this point, the system assumes that it actually have all the data and starts parsing it. Suddenly, the operator realizes that he had made a mistake, so it just goes back and change one of the options for the beam type or the energy mode. And then very fast, by just putting the enter key, just come back to the command line. If this procedure is done in less than 8 seconds, the system cannot realize that there was an update in the input values. Thus, there is an inconsistency in the system and results in a failure that the wrong equipment gets into the beam path. That's one of the major faults of the Therac-25. It took almost 3 years that they could root this fault and realize that because of that 8 seconds, this fault could be simulated and result in a failure. So what were the lessons learned from the Therac-25? First of all, there's a big difference between the safety and reliability of a system. A system could be safe but not reliable, which is, for example, if a system which is not functioning is a safe system but may not be reliable. Or a system could be highly reliable but not safe, like the Therac-25 system. And the lessons from the system were also the manufacturer had overconfidence in the software. They never tested the system very in detail. There were little documentation. There were unrealistic risk assessment. They had some software reuse in some parts from the Therac-20 version, which were not tested accordingly to the new version. And they couldn't, they didn't have a well-defined process for eliminating the root cause of failure. So this actually brings us to the point that since the failure of the medical devices may result in serious injury which are like, and may cause death or even more than that, or serious injury for the patients, there should be authorities to regulate these medical devices. There are two big authorities that are responsible for this issue. One of them is FDA, and the other one is the legal system. So I had this overview of the FDA in my previous presentation. I went through the details of the FDA regulation process. Here, just a brief overview. So whenever a manufacturer wants to market a product, it should submit a pre-market document to the FDA for the approval. What does this document include? It includes the level of concern of the product, which means that if the product malfunctions because of any reason, what could be the level of the injury which may result because of the malfunctioning, which could be a minor, moderate, or major. And then the pre-market submission also includes the, for example, software description, the design document, the traceability analysis, and so on. So we also covered another part of the FDA regulation, which is the risk management for the system, which includes two big categories of risk analysis and risk control. The risk analysis includes the hazard analysis. That means that we have to find what are the hazards of a specific medical software, what are the root causes, what has been done to reduce the level of the, if the hazards get executed, then how can we control that? And also the risk estimation, what's the risk associated to each hazard? And also the risk control, what are the actions are performed to mitigate the level of the risk to an acceptable level? So now, beside the FDA, we have this legal system which also has an authority for regulation, or at least it's a power that makes the manufacturers to be sure that the products are safe. So there are three theories for the liability of the medical systems, which one of them is strict product liability, negligence, and the warranty. Most of you are familiar with the warranty, but getting to the strict product liability and the negligence, we should know that with the strict product liability, okay, consider that you are a person who are injured from a medical device because of the malfunction of a medical device. So to make a case and go to the court, you should be able to prove that the company who manufactured the system were careless during the production of the system. But it's not easy for an individual to prove this, that the company was careless in manufacturing system. That's the reason the law made this rule, which is strict product liability, that focuses primarily on the medical device itself. So in that case, you just have to prove that this is the manufacturer of this device, and that device caused the injury. And that's it. So you can sue the company for the injury. The other one is negligence, which focuses on the manufacturer and the distributor beside the product. So it does not just focus on the product itself, which is the case for the strict product liability. So this rule, the strict product liability, allows a person which is injured because of a medical device or even a drug to recover the compensation from the liable manufacturer without showing that they were really careless. So they just have to prove that the product was defective. They don't have to prove that the actual process was a careless process which resulted in that fault. So and besides, they have to prove that the foreseeable risk of harm posed by the device are sufficiently greater than the foreseeable therapeutic benefits of that specific device. And now going to negligence. So in having a case that you want to prove because of the negligence, first of all, you have to show that the manufacturer has owned a duty to the consumer, that they had a duty for making their device safe, and they could make the device safe, and they didn't do that, and that resulted in an injury of a patient, and they should be able to prove that, for example, that injury was exactly caused because of that negligence of the manufacturer. And the warranty, it just says that, for example, during the intended period, that in a fixed period, if the products get used for the intended that if the product is actually, it should be safe for the intended use. So you can always say that you didn't use the product in the safe way, but it doesn't come in the warranty issue. So what are the potential liable parties if there is a malfunction of a medical device? It could be the manufacturer, it could be the physician who prescribed the medication, it could be the physician who actually used the medical device during the medication, or it could be even the hospital who employs the physician and nurses for that. Okay, now these are part mostly for the regulation, FDA, and the legal system. Now getting to some technical issues. So now we know that we have to improve the reliability of the software. What are the techniques? I actually covered this before, so I'm not going through the detail of that. We had fault prevention, fault removal, fault tolerance before. So for the fault removal, we discussed verification and validation. We also discussed different approaches for software testing. And for the fault tolerance, we actually, I wanted to discuss on 2 approaches of the fault tolerance, which were end version programming and recovery block. But due to time constraint, I don't have time to go into the detail of these 2 approaches, but you can find more detail in the full version of this presentation. Now going to a case study which considered the failures of a medical device, of some medical devices during the years 1983 and 1997. This data was actually the source of the data was from the FDA, which included about 383 medical devices recalls that none of them caused the serious injury or death, but they led to the recall of the from the manufacturer. This number of software failures were increasing rapidly during the last few years because of the rapidly increasing use of the software in medical systems. So the study, they categorizes the failures by their symptoms, and they try to root the cause of the failure, and then also propose some approaches to preventing those faults in the system. So as you can see in this failure distribution by device panel, about 30% of the failures reported were for the radiology center, about 20% were for cardiology, and then about, let's say, 19% were from diagnostic section. So as you can see, one of the biggest part that may cause a failure is a radiology department, which the Therac-25 actually came in that, were categorized in that part. So the data had some information on how they observed the failure. For example, there was an alarm that should be sound that it didn't work, or the system stopped operation. So they took the symptoms, and they also categorized the failures based on the symptoms. This is what they came with. So as could be seen, about like 29% of the symptoms of the failures were because of just the function. There was a malfunction inside the operation of the system. And then 22% were because of the symptoms was the behavior. They didn't behave as it was expected for. And then 90% was the output of the system was not a correct output. And so they tried to find the root of these failures, and they could categorize it into the usual category of the faults in the system. As you can see, the biggest portion of these root cause were from the logic and because of the calculation faults in the system. They also proposed some approaches for prevention and detection of these faults that they could prevent the system that prevent introducing the error, and also for detection after the error being introduced to the system. So they also proposed some other kind of just research approaches to try to prevent the errors or detect the errors in the system, which could be if having a complete requirement specification, traceability analysis, or even the use of simulation for this approach. So what are the research challenges in this area? First of all, there's a big gap between the software engineering and system engineering that should be covered. There is lots of problem with software specifications since it's not a formal process. And so we can try to actually formalize the specification process by model checking or formal verification or model checking. And then, as I said, the newest approach in the reliability area is the autonomic computing or the self-healing. So just briefly explain what's the autonomic computing. In the autonomic computing, what they say, or which IBM is the initiator of this project, says that usually we don't have a complete specification of the system, so we try to make the system somehow which could be able to fit itself when it's being applied in a specific environment. It has 4 major elements, which are self-configuration, self-optimization, self-protection, and self-healing. So what's the medical device reliability comes to the category of the self-healing, which means that it should be able to detect, diagnose, and repair the localized problem of the bugs of the software. In that case, you should provide some patches for specific bugs that may appear during the execution, and try to adapt the system to heal itself during the operation without the interference of the operator or even shutting down the system. Now, concluding the whole presentation, we presented the safety critical system, which is a category of the medical devices. We discussed the FDA regulation, legal issues of the medical software. Briefly, in my previous presentation and today, I discussed the software reliability techniques and a case study of the medical software failures reported in the previous years. And then what's the research direction in this area? As I pointed out, it could be formalizing the software specification by formal methods, or and then verifying that analysis by model checking. And the newest approach, as I said, is a self-healing or in the autonomic computing area. So these are some of the selected references. Any questions?
So you mentioned self-healing. Is that equivalent to, so self-healing software, is that equivalent to fault tolerance?
Oh, there's a big...
Repeat the question.
Alex actually asked, what's the difference between the fault tolerance and the self-healing? Are they the same? So there's a big controversy right now going on in the reliability community that what's the fault tolerance and what's the self-healing. Fault tolerance is like, the approaches in the fault tolerance are based on the redundancy part. So I didn't actually get to the detail of those approaches, which is inversion programming and recovery block. It's completely based on the redundancy. And however, the self-healing is different. It's first of all, they have to diagnose the fault, which is not done in the fault tolerance part, and then try to repair it. However, the fault tolerance part tries to mask the fault. It does not do any diagnosis. It just tries to mask the fault in the system. But still, some people in the reliability community consider self-healing as a new approach in the fault tolerance.
If we cannot have systems which are created for one specific purpose and make them reliable so as they work safely in healthcare environments, what's the possibility of developing systems which actually heal themselves automatically or autonomically?
By making, the question was that, if I understood it correctly, if we don't know the exact specification of the software, how can we make a self-healing software for a medical system? Is that the correct?
My comment was, if you haven't been able to produce system software for healthcare which sticks and adheres to the functionality which is desired so as it works in a safe way, how can we, what is the possibility of making that software work in an autonomic way?
Okay. For example, assume that you have a software that's being used for controlling the blood pressure, that's continuously controlling the blood pressure. So this software may start degrading from its correct behavior during some time. So because usually how it happens, there are some faults in the system that directly cause a failure, cause the system to come down. But there are some situations that some faults gets into the system, so that the health of the software system gets degraded during the time. So in those situations, these are the main category of the self-healing systems, that you try to diagnose the fault at the first place that it appeared into the system. So before actually getting through the whole system and having the domino effect over the other components of the system, try to diagnose it and, for example, have a patch to put it in the system, try to fix that fault, instead of actually having the system have a cascading effect over all components and gets to the actual failure. But and this is the most important part, because you cannot, we could not have an operator just sitting there and just watching the software just every minute how it's actually operating. So in that case, we could define one of the approaches, which is actually being researched in the university right now, having a kind of threshold or having an index for the health of the software. So when that index comes to an under threshold, we assume that, okay, the health of the software is degrading. They have to do something. So before we get to the actual failure of the system and the whole system just shut down, we could somehow fix the system and make the system to the correct execution path, push the system through the correct execution path.
My question is, what does the FDA bring to the table? What kind of specific, what's their contribution in terms of helping with software reliability? We saw that you talked about the extraordinary failure of Therac-25. So obviously they missed it too.
Yeah.
So what do they bring? What's their contribution?
First of all, for the Therac-25, the question was that what's the benefit of the FDA, or how can the software reliability could benefit from the FDA, especially for the medical devices? First of all, for the Therac-25, it was before 1990 year. So there was a new process which was incorporated in the FDA from that year. So the Therac-25 actually happened before the new submission of the regulation of the FDA. However, as people in software engineering usually agree with this point, that the development of the software is it usually does not follow a very formal process. So every company starts developing a software based on their own software life cycle, even if they actually consider a software life cycle. So FDA, what FDA tries is that to formalize the process, and there's a point that, for example, if you want to market a product, market a software, you should show FDA that you actually followed a formalized process. If you follow a formalized process, it's been proved in different software engineering areas that you're going to reduce the risk of the failure in the system. So just FDA is an authority that pushes the manufacturer to follow a formalized system, because even FDA cannot prove that the system does not have any fault. It just makes the manufacturer to follow a formalized process for making the software. This is my opinion, and this is what I understood from the regulation. Oh, there is another.
You mentioned that the manufacturers of Therac-25 didn't test their code exhaustively, but it's not clear to me that even if they did, they would have found the error.
That's the thing, because you cannot always prove that even you tested the software fully that there is no fault in there are no faults in the system. But however, if the system was being the problem of especially the fault of the Tyler bug was something that could appear in the first round of testing of the software, because it's one of the major issues, which is concurrent access. So if they actually use different test cases, there could come up with some scenarios that showed this specific fault in the system. However, as I said, then FDA cannot prove, nobody can prove that even after software is being applied in a specific area, even after 20 years, maybe in one specific scenario, something goes wrong and it injures a patient or something like that. You can never prove that there is no fault in the system. That's the reason the new approach is like trying to say, okay, we do have a fault. We know that we cannot get rid of all the faults. So what should we do to make the system safe? They try to do masking or even healing the system instead of trying to remove the fault before putting it into the product line.
But with the help of this self-healing process, still there is no guarantee.
There is never guarantees whatever that deals with the software.
It itself is a software, that is trying to heal that. Or is it, how does it?
Yeah, self-healing software is a monitoring software. It's actually monitor the execution of the software system. You can always say, okay, if a software is monitoring a software, maybe the monitor actually malfunction. But since that monitor is a kind of, it could be a it shouldn't be an application specific, first of all. So it could be a specific patch or a specific monitoring system which actually running even on the Microsoft Windows or even on a bunch of software systems right now on the application area. But there are some ways to make the monitor highly reliable. You can make a system highly reliable by redundancy. For example, having 3 servers back up one specific server. But even if we're actually using that in, for example, in all the system, all the products of all the copies of a software, that's going to be very expensive. So they make the monitor highly reliable, which monitors the software system. And in that case, as I said, nothing is 100% in software. Nobody knows exactly what's going on during the execution.
Just unfortunately, time, just to keep on the schedule. I'd like to wonder, would anyone mind if we did the other 2 software reliability ones in a row? Change the order? Because I think it would be interesting to do that, but not